next segment here. Okay, so what we're going on to now is talking about sinusoidal models still. It could be a sine model or a cosine model, and we want to speak of the amplitude, what the period is, and then something called the phase shift. Let's come back to this problem we just did a couple minutes ago, is we had y equals 4 cosine of 3x. We took care of determining the period, which was 2 pi over 3. Then what we want to make sure we do for sketching purposes is we want to take a quarter of the period, which is a quarter of 2 pi over 3, and I'm going kind of quickly here. If you reduce 2 pi over 3 times 1/4, it comes down to pi over 6. We then lay out our graph paper with our period, and then we cut that in half, and then half again to get the quarter cycle spots. So we have pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Is everybody comfortable? Okay. Everybody can do this now with some other problem, okay? In your sleep, okay? Okay. Now, we are then going to lay what kind of a graph on here? A cosine graph. So I'm just going to draw a cosine graph, and we have to know it's fundamental. So I know it starts up on a crest, drops to a node. I'm going to call, I don't think I've used that word much before with you here. That's called a node. It's also called, in this case, a 0, isn't it? Yeah. The 0 of the function. And then it drops to a trough, comes back to a node, and back up to a crest. Once you have those 4 points, do we draw straight lines? Do we draw straight lines? No. We draw a nice smooth curve. Yes?
So that's how you plot the points. It seems like all the other times you would find like the x and the y and plot it that way. So I mean, since it's 4 is the amplitude, you start it's the cosine
the first
function.
point.
You start on the y-axis.
Yeah, because you know what a cosine looks like, right? Starts up here, rolls down, and then back up.
Okay.
Yeah. So I start on a crest if I'm drawing a fundamental cosine. Now notice I haven't labeled that yet, have I? All I'm doing is drawing a cosine. And it's nice and smooth. It's not an absolute value function. It's not a V-shaped looking thing. It's nice and smooth, non-linear. There's one cycle. Yeah. And I simply label this 0, 4. Done. One cycle. What's the range of this thing? Look at the picture.
4 to -4.
-4, always smaller to larger. -4 to 4. I mentioned that earlier. The range, -4 to 4. Always smaller to larger in interval notation. Okay, done with that. Some new vocabulary. Any questions? Everybody okay? Everybody all right? Okay. Okay, new words, new vocabulary. This is called the axis. This is called the axis where the nodes sit. The axis. I also call it the node line, the line on which the nodes will occur. The reason we want to know that is because in about 2 minutes, we're going to take a function like this, and we're going to lift it up or shift it down. Lift it up or shift it down. And that whole axis goes with it when that occurs. You with me on that idea? If I lift this thing up or lower it down, and then what's that going to do to the range? That range is going to shift, isn't it? That range is going to shift. Okay. The amplitude. The amplitude is the distance that a sinusoid can rise or fall from the axis. That's called the amplitude, and it's an absolute value. It's always positive. It's the distance from the axis to the crest or troughs. the distance from the axis or the node line to the crest or trough. In this case, the amplitude is 4. Okay? The period, we already talked about the period. The period in this case is 2 pi over 3. Has this cosine graph been shifted at all horizontally? No. No shift at all on the cosine graph. Okay. So there's something called the phase shift that is 0 here. Make sense? No phase shift? Okay. So new words, phase shift. I'm going to use the book does not have a symbol for that. I'm going to call it capital S, and it happens to be 0. So the phase shift in this particular model is 0. Let's go ahead and get a little bit fancier now, as long as everybody's comfortable here. We'll move on. Okay, let's go over to the other board. Let's do another very simple equation, but very important, and it will tie back to something you did in algebra. I want to do a 30-second review with you on something. Y equals e to the x. You should know that one like your name as far as the sketch goes. Move your hand through the air like e to the x. No, for 90% of you. Okay. What kind of a function is that? That's an exponential function. This is going to take more than 30 seconds. Exponentials grow as a multiple of their base. Most of you seem, where I just saw you waving your hands through the air, some of you were doing parabolas. Some of you were doing square root graphs like that. A few of you did an exponential function growing as a multiple of e, 2.718 approximately. Grows at e to the 0. If you ever get rusty on these, which it seems like you are, plot some points. If you come over here to 1, e to the 1 is the value e. If you get to 2, it's e squared, e times e, growing as a multiple of the base. When you're at 2, it's clear up here. E squared, which is 7 point something. It's growing as a multiple of the base. And so the graph ends up looking like this. Exponential functions always have a horizontal asymptote. In this case, y equals 0. The reason I wanted to use this as an example was to dust off some cobwebs, but also to, let's call this f of x. I wanted to find out what you would sketch for y equals f of negative x. What if you come inside here and change the input to be negative of the input, of the original input? This will always be related to the original f of x. In which way? Right. Oh, correct. Okay. It turns it around like this. Okay? Turns it around like this. There's something somebody told me years ago. The Queen of England will wave like this, okay, when she's going down in her carriage and down the street in her carriage or something, okay? So remember that. F of negative x, turn it around the y-axis, always. F of negative x, always. Start with the original f of x, turn it around the y-axis. So this particular e to the negative x is a model that looks like that. Still having a horizontal asymptote, still being an exponential function. Why did I want to go over this with you? Don't forget this. This is important. Okay. Oh, some of you, let me do one more comment before I continue with this, because this is kind of important. This is kind of a transform thing, isn't it? Isn't that negative x thing a transform? And why not think of it this way? What if I had a number out in front here? What if I had a negative out in front of the original function also? What if there was a -1 out here, or -4? Wouldn't that go down underneath this y as a negative? And doesn't that turn the graph upside down? Right? You're familiar with that. Well, come in here thinking similar to what we talked about earlier today, and think about what that's going to do. That's going to turn that graph around the y-axis. I keep saying this stuff fits together like a glove if you see the patterns. If you see the patterns. Now we're ready to come back to trig after this little review. Here's a new model, a new sinusoid model. We used a cosine previously. Let's use a sine. Let's do this. Quick sketch. Quick sketch. Your normal sine wave you're used to seeing is this. Take that thing and flip it around the y-axis. Right? Flip it around the y-axis. It's going to sit here like this. And you're going to label this point where the crest is. Where? At 3. At 3. And the period? Any change in the period? Still 2 pi. Okay. All right. I'm going to erase this algebra back here. Let's see, I think I have something. How about this one? Y equals 2 sine of minus pi over 2x. Something out of the book. Something out of the book. Y over 2 equals the sine of x over what? In the transform form? -2 over pi. Right? Take this down below as the reciprocal. Invert and multiply brings it back up like the original. Okay? So the period, one thing they didn't show you in the book is the period, the formula they gave you was this, right? And what's going to happen if you memorize that formula and just simply use it, you're going to go, oh, I'm going to put this number in right there, this original omega right up here, right? And if I do that, I'm going to end up with a negative period, which doesn't make any sense. So technically, their formula should have that on it, an absolute value of what you see sitting right here. Okay, and when you do that, this is going to be the same as -2 over pi times 2 pi, or -4, but you're going to take the absolute value of that thing, and you're going to end up with a +4 for the period. But then, to draw the sketch, you're going to do something like this. And what I would do is I would draw myself a sine wave that is turned around because of what I talked about just a couple minutes ago. I just simply turn my sine wave around. So, and it's going to go through a complete cycle like this. Because of that negative, still has the period of 4 you can see here, and it's going to sit here like this with an amplitude of 2 and the period shown right below there. What I would like to do is to see if this is correct, because we make mistakes frequently, don't we? Okay, so what I do then is I go grab my calculator, and let's do that real quickly. I'm going to take this function. What mode should I be in here? Radian measure. So I want real numbers for my inputs here. And these numbers, 1, 2, 3, 4, probably represent something like what? Most likely time. Most likely time. Okay, so real quickly with a calculator, you folks know how to do this. I would check my mode first. And I'm going to get the base on here. Second. There we are. So I'm going to have that on. And then for some reason, we've got a reverse image going on back there at Quentin. He's working on it. So he'll fix that in a second. And so what we're going to do is key this problem in here, which was 2 times the sine of negative pi times x divided by 2. Is that correct? And I'm going to build a viewing window, negative 4 to 4, 1. My amplitude should be 2. So what I want to do is I want to go a little further than that, negative 3, 3, 1 on my y readings. Hit graph, and it better land just like we drew on the board. Otherwise, we have a problem. Okay? How many of you feel that you could do this now, this process of sketching and so forth? Okay, looks like 2/3 of you. Okay, good. That's a good start. Come see me for individual help if you need it. Okay, I need to expand this concept a little bit, because right now all we've done were models like this, haven't we? A sine omega x. So let's expand this and make it a little more complicated, and then I'm going to show you another way to lay out your sketching involving the period. Okay. I hope you're staying with me on this. I'm going a little bit fast, but some of it is review, I hope. Okay. So here's what we want to tackle. Y equals A sine omega x minus Greek letter phi, phi. This is omega plus something called b. And I did something earlier, a few sessions ago with you. I think I did something like this. Okay, something like that previously. Okay, and if you follow that or understood that, then you should be okay here. If you were confused when I did that, I'm going to kind of go back through that logic again with you here. Okay. There's some names here. This is called the omega is called your angular frequency in applications. Angular frequency. And it relates back to this stuff we started the course with, where we had circular motion going on. Circular motion. There's there's an angle occurring as you let something rotate, and the frequency, how often that occurs, you know, like real fast or real slow, okay, it relates to that value right there, omega, which is called as I said, the angular frequency. This angle sitting over here. See, what we have going on is we have omega x as an angle, and we're subtracting another angle from it to create an angle which is this input here, okay, which is the angle inside the sine function. That thing is called a phase angle. A phase angle. That's not too important unless you're going into an area in electronics or vibrational systems, vibrating systems, or possibly in population cycles. Anything that follows sinusoidal modeling, that does have some importance, but primarily in electronics and in vibration theory kind of stuff. So I just want you to be aware of that as a word. And then what's this B over here? What's that do to the graph?
Vertical shift.
Yeah, good. That's a vertical shift, isn't it? Vertical shift. It's going to lift the whole graph, including the axis and the node line, up and down, right? And it changes the range, doesn't it? And then up front here, we have the familiar amplitude. Okay. So what we want to do is practice with a model like this. And just for a completeness on the generalized case here, watch this. If I subtract b from both sides, I get y minus b. And if I divide both sides then by a, I get this. And over on the right side, I just have a sine. I just have a sine sitting there. Now inside there is the omega x minus phi. I want to factor the omega out and take it down underneath. So I've done this before with you with this b and c previously, but I'm going to repeat the algebra right here. What we do is we insert an omega over omega in there with the term phi, and then we're going to factor this omega out in front, right out there, and then left inside is x minus phi over omega, and then we're going to move the omega down underneath. And so for completeness, here is the y activity or business or stuff, and over here we have x minus phi over omega divided by 1 over omega, which we've seen before. This gets pretty wild. Okay. Now look at what's going on here. You know that this b does what? Look here. That's the thing that kicks the graph either up or down, doesn't it? And the A, previous to that, does the vertical stretching or squeezing on the Y, and it might even turn the graph upside down if it's negative, potentially. Okay, and you should be comfortable with those. Similarly over here, the 1 over omega causes the change in the horizontal stretching or squeezing. Probably falling asleep because I've talked about this so many times now. And it might even turn the graph around the y-axis, depending on the value of omega. This phi over omega is analogous to b, isn't it? That's now going to be a horizontal shifting to the right or to the left. And that's what we call the phase shift. Phase shift, I call it S is equal to phi over omega. That's a summary. Oh, and then of course your period is going to be 1 over omega times your 2 pi, or omega over 2 pi. So there's a complete summary of all of the things related to a sinusoidal modeling. Should we practice one with a new way of figuring out how to plot the period and the portions of the period when you chop it up? Okay, so let's build one. You see I hope it's clear to you that I've tried to start relatively simple, where there's some review, and then now we're getting into something that's quite a bit, that's as complicated as it gets, which is pretty complex, okay? That thing we just did. And now we're going to practice one with some numbers. This stuff's becoming real. Okay, it's starting to become more real. So, let's say the tide rises and falls above sea level, above and below sea level. Okay? And let's say it rises and falls 8 feet above or below sea level. And what I want to do is inside the sine function now is I want to use, I'll make it artificial. It's not going to exactly match the tides because the period is going to be different. I'm just going to throw something a little easier in right now instead of us knowing there's 2 tide cycles a day, and we could do it that way, but let's hold off on that. Let's just go in here and throw in, say, 2 pi x minus pi and then let's say there's a surge that has lifted it all up by 2, so plus 2 on the tail end, okay? So, you should be comfortable seeing the fact that the amplitude is 8 and the vertical shift is up 2. So you should be comfortable with that by just looking at the equation. Okay? If you want to see it the way I've shown you previously, it would be this way, subtracting 2 from both sides and dividing both sides by 8. We would have this information tied into y. And then now I'm going to come inside here. And I'm going to do this 2 ways. I'm going to do it the transform way that I've confused you with previously, okay, some of you. And then I'm going to show you another way for those who felt confused, an easier way for some of you to figure out how to actually draw the sketch. So the transform way of this is I'm going to start by making sure that I have a 2 pi term tied in with this phase angle. I don't have a 2 there though. So what I'm going to do is I'm going to tuck a 2 in there with that phase angle pi and make sure I also divide by 2 to make sure I don't change my equation. Now I'm going to factor out 2 pi, and I'm just paralleling what I showed you previously with omega and phi. I'm now going to factor out the 2 pi inside there with the angle, and 2 pi comes out, and I'm left with x minus 1/2. 2 pi and 2 pi factored out, leaving a minus 1/2 right there. Then I'm going to move my 2 pi down underneath. As the reciprocal of 2 pi. And now I have it in the form that I've been showing you earlier. The period is then going to be 1 over 2 pi times the fundamental period of the sine function. So the period is going to be 1. The phase shift is what?
1.
What's the phase shift?
1/2.
Yeah, isn't this a shift to the right of 1/2 right here?
Yeah.
a shift to the right of 1/2. Just like this is a shift up of 2. So the phase shift is 1/2, positive 1/2. Okay. Our objective is to draw a sketch, isn't it? Draw a sketch? Okay. So we're going to be working on that, but I'm going to show you another way here in just a second. So I'm going to have to lay out quarter cycle points, aren't I? Quarter cycle points. So one off on the side, I always do this. 1/4 of my period is going to be 1/4. That's the way I'm going to lay my tick marks out. So I'm going to go 1/4, 2/4 is 1/2, 3/4, and finally 1. I could go, that's 4/4, and then 5/4, and 6/4, reducing fractions as I go. Okay, I went a little further than a period. Everyone can do this, I believe. We'll find out when we have a quiz or a test, okay? Now, I want to show you another way of doing this, of getting those points plotted. How many of you felt like you followed that, tracked with all this? Okay, we've been over this many times. Sometimes people do get balled up in the algebra. There's a few of you still having some trouble, so I want to show you another way to do this. You can come right back up to the original model. And I want you to think of this thing I'm circling here as an angle, right? Which it has to be, since it's inside your trig function. It has to be an angle, doesn't it? You look at your model, and I don't care, it could be any of the 6 models, any of the 6 equations, or ratios. So it's a sine model, so you know this angle starts a cycle on a sine model. An angle starts a sine cycle on a node, doesn't it? At 0? At 0? So if it starts its cycle on 0, then that means this whole angle, I'm going to put a subscript S for starting, has to start on 0. It starts its cycle. That whole angle starts a cycle on 0. Now solve for this starting x value. This is a new x value. So solve for this starting x value. So 2 pi x sub s equals pi. Divide both sides by 2 pi, and we get 1/2. The sine starts its cycle. The sine model starts its cycle here at 1/2. That is your phase shift. That's your phase shift, right here. Okay, starts right there. This is x sub s. Okay, how are you going to find out? Let's say you did not understand any of this transform work we did previously. Let's say you didn't understand any of this transform work. How are you going to find out where that thing finishes its cycle? What do you think you would do with this angle? You know sine will finish a whole cycle if this whole angle here becomes 2 pi, right? Where my hand is. So why not do that problem? It ends a cycle if the whole angle, I'm going to change this to a new x, ending point, equals 2 pi. Right? Not too bad. Now, watch the algebra. I'm going to keep this phase angle separate. You don't have to. You can just do the algebra, right? Move this over and you get 3 pi, and then divide by 2 pi, and you get 1/2, right? You get 3/2, which is sitting right over here, folks. You can do that. But I want to show you a little trick that's very convenient. Why not keep this phase angle separate, move it over here. So you get 2 pi x of e equals 2 pi plus pi. Keep those two parts separate. Now divide both sides by 2 pi, and we get 1 plus pi, whoops, 1 plus what? When you divide by 2 pi? Divide by 2 pi, folks. 1, divide by 2 pi. What do you get there? 1/2. Which is your 3/2. What's this? Isn't that your starting point? And what's this?
Period.
Isn't that your period? Does that make sense to you? If you add a starting value and you add the period to the starting value, you'll get an ending value? Right. Make sense? You got a starting value, and if you add the period to it, you're going to be at an ending spot? Okay. So doing this simple calculation right here and keeping the parts separate, you can identify the period, and you can always identify the phase shift. You can then come down here and plot your points by taking 1/4 of your period, lopping it off like we did, and then go ahead and lay those in there. So then we now have a model that is lifted up to, don't forget the up to, and a multiplier of 8. And so what we've got is we're going to lift this graph up to, so draw this line, y equals 2, that's your axis. Come up onto that axis at your starting point and lay in your node. Lay in your node. Come up onto the axis and lay in the node where it starts and where it ends. And then you know it's a sine wave, and a quarter cycle, it's going to be up on a crest at 8 and on a trough at -6. And back up on a node at 2, and then, hold it, I drew something wrong. Oops, sorry. I never make mistakes, do I? No. Okay. Okay, we're coming up here on our axis, up to, from our where our starting point sits, rises to a crest, back to a node, and then here it's going to be down at -6, and then back up to its node. And there's one cycle of that model.
Why doesn't it drop down to -8?
Because it's lifted up too.
Capiche.
Okay, what's the range of this mess? -6 to 8. Oops.
10.
Thank you. I never make mistakes. -6 to 10 because I get help from you guys. Okay.
I understand that.
Very good. And so what you might have done, folks, here's a handy way also to get your range correct, is think -8 to 8 and then do what to it? Add 2. See that? -8 to 8, add 2 to those, and you get your range.
And if the equation was y plus 2 over 8, then the axis shift would be 2 down from the 0.
Right on. Yep. Yep. Because if that was a y plus 2 here, then that 2 would have gone back over here to the other side as a -2, subtracting 2. Yep. Okay, let's end this segment, and then let's go on to the other data modeling segment for the last few minutes. Yes?